Welcome back to another episode of speech processing. In this video, we will look at machine learning. Let's review real quick the previous lab though. Part of the previous lab was to create a voice activity detector using the NeMo system from NVIDIA, using the AR4 corpus, which is a small subset of larger corpora. And it was already annotated for speech versus non-speech, right? And so you went through the setup, you did the data prep, that is download, install, prep a manifest file, partition the data into training and testing subsets of the data, and you configure the model system to build a MarbleNet model. And then you set up and ran the training with the PyTorch machine learning system, and you ran the test set using the trained model, and you also computed some evaluation metrics and inspected some errors. And that is machine learning. That was machine learning. So let's talk more about that. Let's first talk about traditional programming. So in traditional computer programming, by traditional I mean not machine learning, you have some problem or some task you need to do, and you figure out what the input is and what the output should be, and then you design an algorithm that is a sequence of commands in some programming language that goes from the input to the output, right? Takes the input and produces the output. And you program the computer to explicitly do each step in the algorithm. And you try out the program, you debug as necessary, right? And you evaluate the program, see how well it does. Well, machine learning is the idea, you're probably familiar with machine learning a bit, is to allow a computer to learn for itself and figure out how to solve a specific problem or do a task of some sort. And that is, you don't have to program every last step in order to get from the input to the output. Well, how does this work? Well, computers can learn from many examples called annotated data, if the data are annotated. And they typically need lots of examples, like a truckload of examples, especially depending on if the problem is complex, right? And it's often cast as a categorization problem. Like I have this sound, I need to know if it's a B or a P or whatever other sounds it could be, right? And there are many, many machine learning algorithms out there. Let me just click on this link I have out to a Wikipedia article. Here are machine learning algorithms, just all sorts of stuff. K-nearest neighbors algorithm is an unsupervised one. Anyway, just all sorts of stuff of machine learning algorithms. This is in the outline of machine learning Wikipedia article there. Okay. Oops. So many machine learning toolkits implement these algorithms. So it's not that you have to do it yourself. You don't usually have to create your own new algorithm. You don't. You just simply use some algorithm that is already coded up in some toolkit. And you choose or design, maybe modify an algorithm, or just choose the one that best fits your data or the problem that you're trying to solve. How about machine learning applications? Well, it's all over our modern world, right? And machine learning is just the result of machine learning is everywhere around us. Any problem or any area that has data can lend itself to machine learning applications. So related fields include data mining, artificial intelligence, natural language processing, or NLP for short, computational linguistics, and other stuff, right? Just anything with data can lend itself to a machine learning application of some sort. And machine learning is usually a necessary step for any peer-reviewed article in natural language processing. So here I have, let me remove myself a second. Here I have some graphics I've grabbed from the internet about different machine learning applications. On the left-hand side, machine learning is a part of many different fields. Anything, again, using data. So statistics, physics, neurosciences, just all sorts of any field that has data, right? And on the bottom right of this slide, we have some applications, other applications like autonomous vehicles, self-driving vehicles, Google Ads, advertising, personal assistants, right? Alexa, Amazon Alexa or Apple Siri, etc. Are the result of machine learning models. Filtering systems, like filtering, finding spam versus ham, that is, spam email versus good email. Anyway, recommendation engines, all of this stuff is the results or is an application of machine learning. And here's another graphic I found on a blog post about machine learning, and there are just many different algorithms that can be used, and they're kind of categories that go together, like neural networks, decision trees, and regression, machine learning algorithms, and dimensionality reduction. And these can be combined together into one system. So just a lot of different things. Now, it's not expected that any one person knows every last one of these, or this is not even an exhaustive list. It's not expected that everyone knows everything, or somebody who works in machine learning knows every last algorithm that's out there that they could use. I just simply want to show you here that there are many different machine learning algorithms based on problems. Usually it's the problem or the task that's trying to be solved that kind of dictates or encourages the use of one specific machine learning algorithm. Okay, well, what are the steps to machine learning? Well, the basic idea is to use features to predict some outcome. And you define categorization problems to address. So usually it's categorization. It can be regression as well. But often it's categorization, like, what does this sound? Or here I have a document. What should I label this document as? Is it like a review of a restaurant, or is it a contract, a legal contract, something like that? And you start with some annotated data, right? Data that already has the label. That's training data. And you teach the computer how to do the task, or how to recognize, or how to associate the features of an item with its label. And you do that many different times, like I mentioned. You have as many examples as you can get, really, of training data in order to allow the system to learn the patterns better than humans can, often. And then you test the system to see how well it performs on new input, the testing data. And you evaluate it and document the results. And this is done with various tasks and algorithms. Machine learning systems deal with features and outcomes, what classification ones do. And so you have data, and you try and collect whatever data you can that will help make a decision or make a classification. And you have a list. You list interesting, relevant properties that will be used by the computer. And then you encode each data item as a feature, and each feature has its own semantics. The result is a feature vector, that is a sequence of numbers. Usually it's numbers, or if it's a character, it can be turned into a number. And then the feature vectors are used by the system to do categorization. So how do you get machine learning data? Well, there's quite a few sources out there. Here I have links to quite a few things I just found. The LDC itself, right, the Linguistic Data Consortium that we spent some time looking at in this class, has data sets that can be used for machine learning purposes. For example, here's one, the CMPS one here. This is a corpus of investigation of Spanish in Mexico, developed by the Speech Processing Laboratory of the National Autonomous University of Mexico. I think it's the biggest university in Mexico City. It consists of approximately 18 hours of Mexican Spanish radio speech, associated transcripts, pronouncing, dictionaries, and language models. The goal of this work was to create acoustic models for automated speech recognition. So that was the whole purpose of this project and this data set on LDC. And there are quite a few out there on LDC that have that same purpose, was to just create a data set in order to do machine learning. The European Language Resource Association is similar to the LDC, right? Hugging Face Datasets has a lot of datasets sitting there. Here's Hugging Face, right? There are some options up here at the top. The models are the result of machine learning training sitting right there, but they also have the datasets right there, the second option there, top of the screen. And you can get the actual data, the data set here. So this one is for Open Web Text, an open source replication of the web text database from OpenAI, and it is 12, almost 13 gigabytes. So get all sorts of text. That's just an example. Kaggle datasets has thousands of datasets you could grab. They're not specific to speech nor even language, but you could find some datasets there that deal with speech, perhaps. The University of California, Irvine has a machine learning repository here that it has all sorts of stuff that you could look for related to many different things, including language. The Delve datasets is another website that has some datasets. Again, not necessarily only for speech. All sorts of data there. Amazon Web Services has some datasets here too. Open data on Amazon Web Services. All sorts of stuff. You can search datasets right there. And then the Association for Corpus Linguistics Anthology, we could find some datasets or references to datasets in here. Archive is a scientific website, right, to house scientific papers. There's one for computer science, which has some that deals specifically with language, computation and language, human-computer interaction, other things. And then even there's a Google search for Google dataset search, right? So you can search for this, search for datasets in here as well. So here they are. English, Boston, New York, off-the-shelf datasets, cool. English, Hispanic accented off-the-shelf datasets, nice. Anyway, all sorts of stuff there. And there's a Wikipedia article here, a list of datasets for machine learning research. And there's a big list, as you expect, from, I don't know who last updated this thing, but datasets here, descriptions of what it has. So, where do you get ML or machine learning data? Well, obviously from the web these days, and there's a lot of stuff out there. Let's talk about the basic machine learning development cycle. If you're not familiar with this is how it goes. You have some documents or observations. I'll just use a more generic term, observations with annotations that are used to train a machine learning model right there. And that is used to annotate some raw, unseen observations or documents, and you end up with documents or observations with automatic annotations. So dealing with speech, these would be like 15 millisecond slices of audio file with the label, the annotation being like, what is this phoneme? What does this little slice belong to? It belongs to B. Okay. And then it trains up the model, and then you can use that to annotate, like to ASR, for example. That's kind of the basic development cycle of machine learning. Here's an example of features and outcomes. So let's say, again, whatever data helps us make a decision. Here on the right-hand side, let me make this a little bigger. Let me just edit it on the fly as I'm recording. This should be a little bit bigger so we can see better. Here is a data set. This comes from a paper where they looked at descriptions of restaurants, and each feature here is some aspect of the restaurant, of the description of the restaurant. So for example, does the name of the restaurant have the word restaurant in it? This does not, as Wild Ginger's the name of the restaurant. So we have a 0 for that feature. Does the name of the restaurant have Asian Bistro in it? That is not the case here with Wild Ginger, so we have a 0 there. Does the name have ginger in it? In this case it does, Wild Ginger, so that's a 1. And you just simply go through it. They simply went through and extracted a bunch of features about the descriptions of these restaurants. And they have the target index, like for Asian restaurants here, and created up a machine learning model that categorized the type of restaurant from the description, I think on Yelp, on Yelp. So that's one paper there. And the number of features can be really big, like even millions of features could be used. Even like individual words could be put in as individual features, or bigrams could be put in as individual features, or trigrams, etc. Or even like bigrams of characters, if that's perhaps useful. So that is an example from a paper of machine learning there. And the data types can be either discrete or continuous or both, right? You can have just zeros and ones like yes, no. These are just kind of yes, no's, right? Or they could be continuous like a number, whether a floating point number, that is a number with a decimal point, or an integer, like, the number of, the number of diners per night could be an integer, the average number. Or, the percentage of positive reviews on Yelp, that could be another feature or something. Right, so you end up with a feature vector here's the feature vector, the ones and zeros in this example, and then you have the label or the outcome right there that's associated with that feature vector. And those feature vectors and the label are used by the system, the machine learning system, to do categorization. Okay. And so trying to figure out what features to use is an important part of machine learning, and that's called feature engineering. And it's a non-trivial task to figure out what features should be used in machine learning application or machine learning task. And trying to build programs, for example, Python scripts that extract the features out of some observation is an important task as well. And it's difficult and time-consuming and requires expert knowledge about the task at hand and what features might be useful. And with speech, it's usually often just MFCCs that we saw for each little slice of sounds, overlapping slices of sounds is the most common, or the LPCs as well there. So here's another diagram from another book where you have input, you have a feature extractor to extract out the features, and then you end up with the feature vector for this one observation. Again, it could be more than just 7, there are little 7 boxes here, but that could be many, like thousands perhaps, of features in that feature vector. And the label goes in here, and it goes into the machine learning algorithm, and you end up with a classifier model. And then with prediction, so that was the training stage at the top part. And then with prediction, you have input, you do the same feature extraction with the same feature extractor as you use with the training, end up with features, and then based on the model, it says, I think the label for this is that, whether it's the Asian restaurant or it's the sound buh or whatever task you're doing with machine learning. There are quite a few machine learning toolkits out there. Here I have some. You can take a look at these. Weka, for example, is machine learning software in Java. Mallet is machine learning for language toolkit, Java-based package for statistical and natural language processing, document classification, clustering, topic modeling, and other things with with natural language processing. NLTK is natural language toolkit, written in Python. I use this a lot and teach this in other classes in depth. This one here, the Timbal, I think is how it may be pronounced, is from a university, I believe, in the Netherlands, is an open source software package implementing several memory-based learning algorithms. Cool. Scikit-learn is a popular one in Python as well, machine learning Python. NVIDIA, there's they have all sorts of stuff, right? And they have software as well as hardware. They make hardware, but also software. NeMo, as we know, comes from NVIDIA. And then PyTorch, on PyTorch here. And then ASR systems have machine learning, or the result often, the result of machine learning algorithms. We've seen these when we saw ASR systems. Let's talk about degrees of supervision with regard to machine learning algorithms. Supervised is there's human annotated labels that are associated with vectors, with features. And therefore it requires a human to get in there and actually look at them, look at each one and say, okay, this document is Asian, good. This sound is buh, whatever. And unsupervised, but there's no human supervision. For like K means clustering, the system discovers categories just looking at similarities and differences between data points. And then semi-supervised is you give some small amount of supervised data, and then you bootstrap, that is randomly select samples with more data that hasn't been hand verified or maybe only spot checked. There's an interactive way as well where the system prompts the user to interact with it to actively learn what's going on in the data. So there are different degrees of supervision. The most common, I don't know if the most common, but the supervised one is the one that I feel is most common with human annotations. Evaluating machine learning. It's important to be able to evaluate the usefulness or the accuracy of machine learning systems, so that you know if it's worth using, how well it would do out in the wild with new unseen data. So having some objective method to analyze how useful or how accurate the machine learning system, it's important to have those type of measures. And precision and recall and the derived F-score from those two first ones are really common measures that can be used that you'll see with machine learning, as well as just kind of information retrieval systems, or like searching through text, trying to find the past tense in English through a bunch of text, and you just search for ed at the end of words, that you're going to get stuff that's not actually past tense, and you'll miss some stuff that is past tense but doesn't have ed. So, being able to measure how accurate your searches or your machine learning system is important. Now, precision is the first one here. It's one form of accuracy, and it's the degree to which the answers given by the system are correct. So all the answers that the system gave, how many of those are correct? And then recall, the second one here, another form of accuracy, is the degree to which all correct answers were covered or retrieved by the system. So of all the answers it should have gotten out in the data, how many of those did your system get? And then an F-score or an F measure is a single score that combines those two with this simple formula. In this mathematical formula, you take the precision, multiply it by the recall, hold on to that number, then take the precision and add it to the recall, take that sum, right? So you have this product divided by this sum, and you times that by 2. That gives you what's called the F measure or the F score. And it's a single value that combines those two into one. And these metrics are often used in NLP tasks, including speech. And often machine learning toolkits will have a whole subsystem just for managing evaluation of the machine learning system that is created with the toolkit. So here's some examples just to clarify a bit more on what precision, recall, and F-score are. Precision, again, is of all the stuff that the system gave back, how much of it was correct. And that could be here in purple. If you look at this graphic here in purple, our computer, our system, returned this stuff. And only about 55% of this purple circle falls within the larger green circle. The green circle is what we wanted to get back. And so the precision is about 55%, because about 55% of this purple circle falls within the green circle. That's precision. Recall, again, is of all the stuff that I should have gotten back, how much did my system actually give me back? And it looks like this overlapping American football shaped Venn diagram thing is about 40% of the green circle. So my system only got about 40% back of what it should have gotten. And then if you just do the math I just described, you get an F-score of 0.46. Here's another hypothetical scenario here, where in purple we have what our system gave back, and everything it gave back was correct, and so the precision is all the way up to 100%, or 1.0. But we missed about 20% of what we should have gotten back, give or take. See that? So we missed some of the green stuff. And so our recall's at 0.8, and then our F-score is about at 0.89 if we round up to 2 digits. Okay? And then this system right here is the worst, where everything that our system gave back was incorrect and we got nothing back, right? Got nothing back. So the precision is 0, because everything that was given back by the system was bad. And the recall was 0 because we missed everything we should have gotten. And I don't even know how to calculate the F-score, because if you divide by 0, you get infinity, but 0 divided by 0, I don't know. It's just 0. There are some other metrics to measure how well machine learning algorithms do, machine learning systems do in natural language processing. The word error rate is simply the number of substitutions or deletions or insertions of characters or phones, in our case, divided by the total number of phones. That gives you the word error rate. The lower the word error rate, the better. Meaning the fewer substitutions or deletions or insertions of phones in a sound, or excuse me, in a word, the better. But with some languages like Chinese, for example, having a character error rate is the way you have to do it there, right? Because the word error rate implies that there are, phonemes in the word that make up the word. But in Chinese and other languages, that may not be the case. So you have to look at a character error rate, or you can get an utterance error rate, just simply like the whole utterance. Was the response to this utterance correct or not? A very high level. You can also look at the true positive rate versus the false positive rate with these formulas here. So just to be aware, there's other metrics to measure the accuracy of speech processing, machine learning models, as well as machine learning in general. Here's another metric here, the area under the curve versus the rater operator. What does this mean again? Here's a Wikipedia article, the receiver operating characteristic. The basic idea is that a receiver operating characteristic curve, or ROC curve, is a graphical plot that illustrates the diagnostic ability of a binary classifier system as its discrimination threshold is varied. The method was originally developed for operators of military radar receivers starting in 1941, which led to its name. Good. The ROC curve is created by plotting the true positive rate on one of the axes against the false positive rate on the other at various threshold settings. Okay, well, anyway, so that's the idea here, is looking at the bottom right of the screen of this slide right here, the bottom right plot first, we see that we have on the y-axis, we have the true positive rate or sensitivity. And so we want this to be high. Like a perfect classification would have 100% true positive rate classification and 0% of false positive rate. That would be the perfect classification system. So we want to be above this diagonal, right? Diagonal means that there are as many true positive outcomes as there are false positive outcomes. We want to be up on the top left triangle here. So system A and system C are doing pretty good. System C is doing the best because it has the highest true positive at about 0.75 and the lowest false positive at about 0.1. Anyway, well, that's C bar. Oops. C bar versus C. So the idea is that, we want to minimize, right, the false positives and maximize the true positives. There's another metric on another way to do that with this graph here. There's another way called detection error trade-off. It plots false negative rate, missed detections that it missed, versus false positive rates that are false alarms or false hits. And so we want to minimize both of those. We want the lines, for example, these two systems or two methods, right? The greater the line is to the right, the top right, the worse the system is. So the farther down to the bottom left, the better the system is. Okay, so the next lab is to choose one or more of several machine learning tutorials. I give you 4 tutorials, and you choose one or more, 2 of which deal with sounds, and the other 2 don't deal with sounds. And so just work through a Colab tutorial and understand what's going on, inspect the output, and then I'm asking you to write a bit more than I have asked you to write in the past in order to motivate you or force you to make sure you understand what's going on with the machine learning tutorials that you choose. Okay, so we'll see you next time.